In machine learning, we're almost always told there's this painful trade-off, right? You can have accuracy or you can have speed. But what if you didn't actually have to choose? Today, we are going to unpack the incredibly elegant ideas behind a model that trains up to 20 times faster than its rivals, and it does it without sacrificing performance. It really is a masterclass in smart optimization. So let's start with a puzzle. We have these amazingly powerful models called gradient boosting decision trees. You've probably used them, but on big data sets, they can be, well, painfully slow. The real question is, what is the machine actually doing that takes so much time? And is there a clever way to get all that time back?
And this brings us right to the core of the problem, a huge computational bottleneck. I mean, anyone who's ever trained a large model knows this feeling. It's that feeling of watching a training progress bar just barely move for hours, or sometimes even for days. So let's look at what's really causing that massive slowdown.
Okay, so imagine you've got millions of rows of data, maybe thousands of different features. To make just one decision in one tree, the model has to exhaustively check every single possible value for every single feature to find the absolute perfect place to split the data. It's incredibly thorough, for sure, but as your data gets bigger, this process becomes punishingly, brutally time-consuming.
So to really understand how LightGBM completely shatters this bottleneck, we first need to build up a little intuition for how these models learn in the first place. Let's take a quick look at the core engine of what we call gradient boosting. The best way to think about it is like you're building a team of specialists. The first one, it's just a simple, weak tree, and it makes a rough guess. Then we look at where it went wrong. The second specialist you bring in, its entire job is to predict and correct the first one's biggest mistakes. Then the third specialist comes in and corrects the mistakes that are still left over. And this just keeps going, with each new tree joining the team to fix the errors of all the trees that came before it, until their combined prediction is super accurate.
Now, the technical term for these mistakes that each new specialist tries to fix is the gradient. And I know that sounds a little technical, but the idea behind it is actually super intuitive. You can just think of the gradient as a little signpost for each and every data point. A really big gradient points to a big error. It's basically shouting, hey, pay attention to me, you're getting me very, very wrong. A small gradient, on the other hand, means the model is already pretty close to the right answer. And this idea that some data points have way more to teach the model than others, that is the key to everything that comes next.
So, if the big bottleneck is scanning all the data, the most obvious solution in the world comes to mind, right? But you know what? It's a trap. I mean, it is a very tempting idea, isn't it? Just take a random scoop out of your giant pile of data and train on that. It would definitely be faster. But what's the hidden cost? What are we really giving up when we do that?
Well, here's the problem. A purely random sample can really hurt your accuracy. Because by being random, you might accidentally throw away the most informative data points. You know, the very examples with those huge gradients that the model needs to learn from the most. This creates a whole new puzzle. How can we sample the data in a smart way? We need to shrink the data without losing the most critical information.
And this is where the absolute genius of LightGBM comes into play. Instead of some brute force solution, it uses two incredibly elegant ideas to attack the problem from completely different angles. Let's break down the first one.
The first breakthrough is called gradient-based one-side sampling, or GOS for short. The core insight here is that not all data points are created equal when it comes to learning. Some are already pretty well understood by the model, those are the easy ones, but others are the source of most of the error. GOS makes a simple decision. Let's focus on the error.
The authors of the original paper, they put it perfectly. They realized that the information gain, which is just a measure of how much a split in the data helps the model learn, is dominated by the instances with those large gradients. It's kind of like a teacher who focuses on the students who are really struggling with a new concept, because that's where the most learning is going to happen. If we focus our computational effort there, we can learn so much more efficiently.
So here's how it works in practice. First, GOS finds all the examples the model is getting really wrong. You know, the ones with the biggest gradients. It keeps all of them, no questions asked. Then from the rest of the data, all those easy examples, it just takes a small random sample. This by itself is a really intelligent way to shrink the dataset, but it does one more incredibly clever thing to make sure it doesn't hurt the accuracy. To make up for the fact that it's only taking a small sample of those easy examples, it gives each one of them a bigger weight. It basically turns up their volume. So in an example from the research paper,
If we keep, say, the top 20% of the hard examples and only sample 10% of the easy ones, each of those easy examples gets an 8x weight. This makes sure that together, they still represent the larger group they came from, and it keeps the overall data distribution the same. It's just a beautifully simple way to get the best of both worlds.
Okay, so Gauss shrinks the number of rows the model has to scan. The second breakthrough, which is called exclusive feature bundling, or EFB, cleverly shrinks the number of features.
The whole idea here is that in a lot of big data sets, many of the features are mutually exclusive. For instance, a single row of data can't be both is a cat and is a dog. So why are we treating them as two totally separate features? Think about it like you're packing a suitcase. Instead of packing a dozen individual tools, you'd put them all into one compact toolkit. EFB does exactly that for features. It bundles these sparse, exclusive ones into a single denser feature, and that dramatically reduces the search space for finding the best split, making the whole thing so much faster.
So the theory behind both GOS and EFB is just beautiful. It sounds fantastic on paper, but the real question is, does this stuff actually work in practice? Let's take a look at the evidence from the original paper.
And here it is. This is the payoff. This table shows what Gauss and EFB actually deliver in the real world. It's comparing LightGBM's training time to other really powerful methods, and the results? They're just staggering. On some datasets, we're seeing speedups of over 20 times. And look at that bottom row, the KDD10 dataset. The other methods ran out of memory. That's what OOM means. But because LightGBM so intelligently reduced the data in the feature space, it handled it no problem.
Okay, so it's crazy fast. But what's the catch, right? Did they sacrifice accuracy to get all that speed? Well, this is the crucial point. Look at this chart. It shows the accuracy on one of the test datasets. LightGBM, with both Gauss and EFB turned on, achieves virtually identical accuracy to the much slower, more exhaustive methods. It's faster and it's more efficient, without a meaningful trade-off. It's pretty amazing.
So what are the big ideas you should take away from this? I think there are two really powerful mental models you can use for almost any optimization problem. First, focus on the error. Don't treat all your data equally. Find the examples that are causing the biggest mistakes, because that is where the real learning happens. And second, shrink the problem, not just the data. Before you start sampling or throwing away data, take a step back and ask, can I reframe the problem itself, like bundling features, to create a smaller, smarter search space to begin with? LightGBM is really a masterclass in this kind of targeted, intelligent optimization. It teaches us to find the real bottleneck and then think creatively from first principles about how to solve it. And that leaves us with a really interesting question. As we face data sets that are bigger and denser and more complex than ever before, what's the next bottleneck going to be? And what will be the next brilliant breakthrough?